While Boeing is still trying to put out the fires, literally and financially, of a crisis that has lasted more than 5 years, Elon Musk is busy with something that promises to be a game-changer: a supersonic, vertical takeoff electric plane, ready for mass production. The revelation took the industry by surprise. It's no longer a futuristic concept or technological fantasy. Tesla, known for disrupting entire markets, has just finalized the design of a jet that, on paper, promises to fly 2,400 kilometers with zero emissions, land vertically, and cost less than imagined to operate. It sounds like science fiction, but the testing phase is already knocking on the door. Since 2019, Boeing has lost more than $32 billion primarily due to serious technical failures, delays, and safety scandals. While the American giant tries to regain public trust, Tesla emerges with a disruptive alternative, free from legacy and outdated aviation paradigms. It's precisely this freedom that allows Elon Musk to think big. Silent flights, without fossil fuels, and with operating costs reduced to a fraction of the current model. This isn't a simple modernization. It's a complete reinvention of the logic of commercial aviation. The number of planned units is also impressive. Musk has hinted that he intends to manufacture up to 10,000 aircraft, a number few competitors would dare promise without decades of market experience. Interestingly, this scale isn't just ambition, it's part of the strategy. By applying the same mass production model used in Tesla's electric cars, the unit cost could drop dramatically, making the aircraft affordable even for regional airlines, air taxis, and logistics services. The idea is to bring the skies to the same pace of innovation that has already taken over the streets. But what gives Musk so much confidence in an industry as regulated and conservative as aviation? The answer lies in technical boldness and the courage to abandon everything traditional. Instead of adapting the current model, Tesla created an entirely new concept. The plane was designed from scratch to be electric, vertical, and efficient. No repurposed turbines or structures inherited from older jets. Every screw, every aerodynamic curve, every design line has a single goal: to fly far, fast, safely, and with minimal fuel consumption. And what about performance? According to the engineers involved, the initial range should be 1,500 miles, about 2,400 kilometers, which already puts the model at an advantage compared to several short-haul regional and international commercial flights. But it's not just the range that's impressive. Vertical takeoff allows landing in confined spaces, such as heliports or urban areas, without the need for long runways. This opens up unimaginable possibilities: travel between cities without relying on traditional airports, faster connections, and even point-to-point flights in rural areas. The impact of this goes far beyond the aviation industry. Consider tourism, logistics, public safety, and even the way cities will be organized. Tesla isn't just creating an aircraft. It's creating a new, invisible infrastructure, a new way to shorten distances at a reduced cost and with a virtually zero environmental footprint. And if the promised 10,000 units comes to fruition, we'll be talking about a volume that could completely alter global air traffic, decentralizing hubs and creating routes where there's currently no demand due to a lack of economic viability. Meanwhile, Boeing remains stuck in the past. Its aircraft are still based on technologies that were once revolutionary, but are now too heavy, costly, and complex to meet the industry's new environmental and operational challenges. Tesla, on the other hand, plays by its own rules. It enters the game with embedded artificial intelligence, modular electrical architecture, distributed propulsion, and a design philosophy that prioritizes extreme efficiency over traditional prestige. And this is scaring many in the industry. More than just frightening, it's forcing competitors to rethink their strategies from scratch. If Tesla can truly deliver a functional, safe, and licensed aircraft by 2026, the world will witness not only the birth of a new transportation model, but the end of an era dominated by a few companies. And in this new scenario, those who fail to keep up with the pace of innovation run a serious risk of disappearing from the map, flying straight into obsolescence. To understand how Tesla managed to turn an unlikely dream into something so concrete, we need to delve into the mathematics and engineering behind this feat. Most people have never heard of the Breguet equation, but it's practically the foundation of modern aviation. It determines an aircraft's range by taking into account factors such as fuel consumption, aerodynamics, and weight. However, this formula was created for kerosene-powered aircraft, where the fuel is burned during flight, making the plane lighter over time. And that's where Tesla completely changes the game. Because electric batteries maintain a constant weight, unlike tanks, which gradually empty, Tesla had to rewrite the logic of the Breguet equation. While a Boeing 737 burns up to 50,000 pounds of fuel during a trip, Tesla's plane maintains a nearly constant mass from start to finish. This, previously seen as a problem, has become a strategic advantage when combined with 95% efficient electric motors, in contrast to jet engines that barely reach 40%. But the real magic happens when you look at the lift-to-drag ratio, basically how much the plane flies relative to how much the air holds it down. Traditional jets typically operate at a 17.1 ratio. Tesla's plane, thanks to its extreme aerodynamic design, reaches 25.1. This represents a nearly 50% gain in aerodynamic efficiency alone. It's as if the aircraft gains extra miles without needing a single drop of extra energy. A silent advance, but with a brutal impact on results. Another interesting point is specific energy consumption. While conventional engines consume between 0.5 and 0.7 pounds of fuel per pound of thrust per hour, Tesla reduced this to between 0.15 and 0.2 pound equivalents per hour. This is possible because electric motors are lighter, more responsive, and waste less heat. With fewer losses, the plane flies further with less. It's not just energy savings, it's a paradigm shift that challenges the conventions of aeronautical engineering. The combination of an ultra-efficient engine and refined aerodynamics results in something unprecedented, an airplane that can travel 1/500 miles using the equivalent of just 20,000 pounds of energy, while commercial jets need more than twice that amount to travel shorter distances. The Breguet equation, previously used as a kind of physical limit, has now become an optimization tool in Tesla's hands. And it's not theory. The simulation data, wind tunnel tests, and computational studies are already in the hands of the FAA. This reinterpretation of the laws of physics shows how Tesla isn't simply trying to compete with the aviation giants. It's playing a different game. A game where numbers are shaped by possibilities that previously seemed unfeasible. Tesla doesn't want to defeat what already exists. It wants to completely change what's possible. And the most curious thing is that the industry's own engineers are having to relearn concepts they once considered absolute. Tesla also leverages the advantage of constant weight to create more predictable and safer flight paths. Because there are no variations in the center of gravity caused by fuel burn, stability is greater from start to finish. This allows for more refined flight control, making it smoother and less susceptible to human error or instabilities caused by load imbalance. This factor, overlooked by many, is key to ensuring safety and comfort in electric flights. In the end, what seemed like a limitation, the battery's fixed weight, becomes a technical asset when combined with design intelligence and mastery over each variable involved. Tesla didn't just break a technical barrier, it showed that, with the courage to question what's taken for granted, it's possible to go beyond what the book said was the limit. And this paves the way for new innovations that, until recently, seemed like the stuff of science fiction. If Tesla reinvented the Breguet equation, much of this feat is due to the meticulous work on the wings. At first glance, they seem too compact for something so ambitious. With a wingspan of just 50 feet, almost half the 93 feet of a Boeing 737, many would bet that this plane would never have sufficient range or stability for long flights. But then comes a concept that few outside of engineering are familiar with: distributed propulsion. And Tesla has taken this to a new level, transforming a physical limitation into a strategic advantage. Instead of using two large engines like traditional airplanes, Tesla positioned between 8 and 12 electric motors along the wings. This arrangement creates a phenomenon called blown wing, or blown wing, where the airflow driven by the engines significantly increases lift and reduces drag. In numbers, 50% more lift and 25% less drag. The result? Small wings now behave as if they were much larger, without the extra weight that would otherwise entail. This completely changes the aircraft's flight performance. But the engineering didn't stop there. The structure of these wings was developed with advanced carbon fiber composites, replacing traditional metal components. This reduced the weight of the wings from about 1,000 pounds to just over 600 pounds, without compromising structural integrity. This lightness allows for aspect ratio, the ratio between the length and width of the wing, of 10:1, which means aerodynamic efficiency close to that of high-performance gliders, something rare in commercial aircraft. The most intriguing difference, however, is the adoption of variable geometry. Tesla's wings are capable of adjusting their shape during flight. When the aircraft reaches cruising speed, the engines partially retract and the surfaces adjust to reduce parasitic drag by up to 38%. This is a gigantic technological leap, comparable to what supersonic fighter jets use, but now applied to a quiet, electric, commercial aircraft. Everything is designed to optimize performance in every phase of flight. Simulations showed that by combining this active geometry with the blown wing effect and ultralight materials, Tesla achieved a total drag coefficient of just 0.25, compared to 0.23 for its competitors. This may seem like a small difference, but in aviation, this represents hundreds of kilometers of additional range. And all this with lower energy consumption than a traditional jet over half the distance. This combination of stacked technological capabilities demonstrates complete mastery over every aspect of flight. One detail few people discuss, but which makes all the difference, is how these wings work with vertical propulsion. Because they're compact, lightweight, and responsive, they facilitate the transition between vertical and horizontal flight. This solves one of the biggest problems faced by VTOL aircraft: aerodynamic balance during axis shifts. In practice, this means Tesla's aircraft can take off vertically, like a helicopter, and transition to level flight smoothly, safely, and efficiently, something many prototypes have failed to achieve to date. This technical expertise also contributes to drastically reducing noise during takeoffs and landings. The engine distribution, combined with the lower rotational speed of electric engines, creates an acoustic profile ideal for urban use. Instead of turbine explosions, the sound resembles the low-pitched drone of a larger-scale drone. This opens the possibility of deploying takeoff hubs in metropolitan areas without impacting the surrounding area, something previously impossible with conventional jets. Looking at all of this together, state-of-the-art materials, intelligent propulsion, active aerodynamics, and digital control, it's clear that Tesla's plane isn't an adaptation of something existing. It was designed from the ground up to function as a logical extension of the electric revolution, a product where every detail was engineered to take full advantage of a system that doesn't rely on fossil fuels, deafening noise, or miles of runway. And it's this kind of thinking that truly threatens the reign of giants like Boeing. With wings that mold to flight and engines that defy traditional physics, the next hurdle seemed to be bureaucracy. After all, Tesla now had to face the FAA, the American agency that regulates everything that flies in the country. And there's no easy way to do it. The basic rule requires that any commercial flight have a certified human pilot, with at least 1/500 flight hours. This requirement is inflexible. There are no shortcuts, and it was precisely this requirement that kept planes like the 737 MAX grounded for years. But Elon Musk didn't get this far by playing by the rules. He changes the board. Instead of engaging in direct confrontation, Tesla opted for a masterstroke, starting flights within the regulations called Part 91, aimed at experimental testing. It's like getting a provisional license to drive a new car. It allows you to test, refine, and gather real-world data without immediately being subject to the stricter regulations of commercial use. This extra time, combined with recent advances in electric aircraft regulation, allows Tesla to race against the clock to prove that its system is safer than the current model. What works in the company's favor is the massive database it already possesses. With the autopilot system in its cars alone, Tesla has collected data from over 10 billion miles driven in real-world environments. This translates into thousands of extreme situations, autonomous decisions, and instant adjustments that would take humans minutes to process. The company is taking this same decision-making engine to the skies, with AI trained to react in milliseconds to any anomaly, from wind gusts to system failures. Another strategic move for Tesla was not to go all in on full automation right away. Instead, it created a hybrid system where AI handles the primary flight operations, takeoff, navigation, and landing, and humans monitor everything remotely via Starlink satellites. Latency, or response time, is just 100 milliseconds. It's like playing a video game with fast internet, except instead of a joystick, operators control electric jets crossing the country in absolute silence. This intelligent approach meets the FAA's requirement that there always be a pilot in command. Takitans. The difference is that this pilot doesn't need to be physically inside the cockpit. He or she can be in a control center with full access to the aircraft's systems, ready to intervene if necessary. And most importantly, with redundancy at every layer of the system. From backup batteries to parallel decision-making systems, everything is designed so that no single failure can bring down the aircraft. The goal is simple: make every flight safer than a trip to the airport. Tesla knows it will only get full approval if it proves its systems exceed current standards. And that means meeting, or even exceeding, the AC 23.1309, which requires that catastrophic failures have a probability of less than 1 in a billion flight hours. An almost absurd goal, but one that Tesla believes is achievable with AI